Let's do this. Over the past week or two, we have looked at the idea of a limit as x approaches a certain value, as x is getting closer and closer to a certain real number a. But we can also examine the behavior of a function as x gets closer and closer to infinity or negative infinity. And we're going to see situations where the function is getting closer and closer to a certain number. And in these situations, we will call these limits at infinity. So let's start with an example. Explore the behavior of f of x equals x squared minus 1 over x squared plus 1 as x gets arbitrarily large. So we're going to make a table of values to see what happens as x gets larger to our function f of x. And so we can start with small values. Let's start with 1, and then maybe 5, and then maybe 10. And then let's look at what happens when x is 100 and 1,000. So instead of x getting closer to a single real number, we're looking at what happens as x approaches infinity, meaning as x is getting larger and larger and larger. So if we plug these into a calculator, when x is 1, well, actually we don't need a calculator for this. 1 squared is 1, and 1 minus 1 is 0. So the function value there is going to be 0. When x is 5, we don't need a calculator for this either. 5 squared is 25. So we've got 25 minus 1 over 25 plus 1. So that's 24 over 26. And actually, we do need a calculator for a decimal approximation of that. That gives us 0.923077. And then for the others, I'm just going to plug them into a calculator. You know the drill at this point. For 10, we get 0.980198. For 100, we get 0.999800. And for 1,000, we get 0.999998. So if you look at the function values as x is getting larger and larger, as x is approaching positive infinity, you can see that the function values are very much approaching 1. And because of that, we can say the limit as x approaches infinity of x squared minus 1 over x squared plus 1 is equal to 1. That is our first limit at infinity. But here's an interesting thing. If you look at this function, the only time x appears is when x is squared in the numerator and denominator. And if we square a negative number, we end up with a positive result. And so even if we took -1 and -5 and -10 and -100 and -1,000, we would end up with the same results. This is an even function. Doesn't matter if x is positive or negative, we get the same answer. And so if we look at what happens as x goes from -1 to -5 to -10 to -100 to -1,000, we have the same behavior. And so we can also say that the limit as x approaches negative infinity of x squared minus 1 over x squared plus 1 is also equal to 1. So in both directions, towards positive infinity and negative infinity, we have the same limit. Let's take a look at the graph of this function to see what's going on. Okay, I've moved these limits over a little bit to the left to make more room for this graph, because I also want to be able to do some things below. But here we can see the graph of our function. And I mentioned it was even, and we can see the graph shows us that's true. We've got mirror images on the left and right. And as we take our x values and make them larger and larger, we can see that the y values are getting closer and closer to 1. In fact, they are asymptotically approaching 1. And the same is true in the negative direction. So this is why we end up having these limits, because you can see the function is getting closer and closer to 1 in both directions. Now, these are limits at infinity, but of course we want an actual definition of what a limit at infinity is, so let me give that to you. Let f be a function defined on some open interval from a to infinity, right? If we want to know what's happening as x is approaching infinity, we need it to be defined on some open interval that goes towards infinity. Then the limit as x approaches infinity of f of x equals capital L means that the values of f of x can be made arbitrarily close to L by taking x sufficiently large. So remember with our delta epsilons that we saw with the precise definition of a limit, what that means in this case is that for any epsilon greater than 0, for any positive distance away from our limit, we can take a delta that's large enough such that if x is larger than delta, if x is larger than a certain number, then the distance between our function and that limit L is less than epsilon. Again, I know a lot of students are usually not super comfortable with deltas and epsilons, so if that went over your head, I don't want you to worry about it too much. It is very similar to the regular limits we've been looking at, but instead of looking at what's happening as x approaches a number, we're looking at what's happening as x approaches infinity, as x gets larger and larger as we're going to the right on the number line. And we can also say the same thing about a limit as x approaches negative infinity. In that case, we need f to be a function that's defined on some open interval from negative infinity to a. So it's got to be defined to the left, basically, at some point. Doesn't matter if there's a point where it's not defined. We just need at some point it to continue being defined moving to the left. So if f is a function defined on some open interval from negative infinity to a, then the limit as x approaches negative infinity of f of x equals L means that the values of f of x can be made arbitrarily close to L by taking x sufficiently large in the negative direction. So again, the simple version of that is, as we move to the left, as x is getting large in the negative direction, our function values are getting closer and closer to that limit, and there's no gap in between that it never passes. It will continue to get closer and closer in that sense.